Hello again. So, so as you saw, we had some technical problem. Good that you are all logging back on. We are sorry about that. So I'm going to give a bit of time for people to log back on and let us know if we have any problems. And meanwhile, if you have any questions, go ahead and ask. Okay, let's continue. So we stated these two theorems. Let's give an example, especially this last theorem. So for example, the limit as x goes to -1 of this rational function because the value of qx at -1 is non-zero. You can see it's 6. Then we can write down the limit using the theorem, and what's the value of the top? That's -1 plus 4 minus 3. The 6 comes from 1 and 5, but this is 0. Okay, question? Okay, so we can calculate limits for any rational function. But let's do an example where we can actually draw a graph and understand what's going on from the graph. So the limit as x goes to 1 of x squared plus x over x squared minus x. So if, well, let's just try and factorize first. So this star, if I factorize, I get this. And I can cancel the 2x minus 1s if x is not equal to 1. So let's do this here. X plus 2 over x if x is not 1. And then this is 1 plus 2 over x if x is not 0. So we can now see the domain of this function. I'm going to do the graph up here. So what are x-intercepts? Well, from here, x-intercepts are minus 2 minus 2 is an x-intercept. So this shows minus 2 is an x-intercept. But when x is 1, the function is not defined. So we have to watch out for that. And then the graph of this function, 1 plus 2 over x, well, from what we learned before, it looks like this. That's right, yes. So this here is the line y equals 1. I'm going to make some more space here, because this diagram became hard to see. So, this is 1. It's also 1. And so at 1, the function is not defined. I'm going to draw a circle to mark that. Okay, so there's some problem with this graph that it's not very well to scale. So let me improve it a little. Okay. Okay. So this is the graph. So the graph looks like same as graph for this, but not defined at x equals 1. And that's what this circle here means. Okay. So then what's the answer? Well, the answer is 3. So that's from the graph. So the limit is equal to 3. And that's true even if even though this is not defined at x equals 1. Okay, so other tricks. To calculate limits. For example, the limit as x goes to 0 of this. So the square root of x squared plus 10 squared minus 10 divided by x squared. So note, again, star is not defined at 0 because of the x squared on the bottom, which equals 0. But Yeah. So if I multiply the top and the bottom by something to simplify the top, so I'll write down what I use and then you can see why it works. So here I've multiplied top and bottom by this same thing. And then what do I get? Well, on the top we have a difference times a sum, so we get a difference of squares. X squared plus 10 squared minus 10 squared. And now we see the trick. That these 10 squares cancel. And if x is non-zero, then my x squareds cancel and I get 1 over just the square root of 10 squared plus 10. Okay, so let's call this double circle like that. No, that's not a very good notation. Let's call this cross. Now, using limit laws, i.e. the theorem above, have that the limit, what was the question again? The limit as x goes to 0 of plus is given by the value of plus at 0. Okay. Okay, so going back. So the limit of star, which we wanted to calculate, is the same as the limit plus by the algebra in the middle. And so the solution is 1 over 20. Okay. So that's some examples of the limit laws. Now let's continue with another theorem. Which is called the sandwich theorem. Now, I always liked this name because Sandwich is a small town in UK, and it's where I went to school. So here it is. And so the fourth L of Sandwich in the 1700s invented so the story goes, the sandwich like that. So probably did not live in Sandwich. It was a military court. For shipbuilding and so on. And he was a military commander. But the idea is he was so busy that he couldn't have a relaxed, normal meal, so he would just have something between bread. Yes. Okay. So the theorem goes like this. Suppose our functions for all x in some open interval AB with C removed. So I'm going to draw a picture of this. So this is x. And this is the value. So the interval is from A to B, and C is removed. So let me write in the numbers A, C, B. And then the theorem is saying that maybe my functions are not defined at C, but they are defined like this. And I have another function which stays between them. Something like this. Oh. Make everything match up on the graph. So this is fx, and this is hx, and this is gx. And now suppose that the limit as x goes to c of gx equals the limit as x goes to c of hx, and that both limits are out. Then the limit as x goes to c of fx is come by out. A remark. This function f is in the sandwich and g and h, the bread. Okay, I'm going to see if there are any questions now. Yes. So I'm going to, reading the questions, I'm going to underline this for all x in AB. So let's call this star. Oh, actually, I made a small mistake from my notation before. So interval AB, take away C. Star must. Star must hold. It's for all x For all x in the interval AB, take away C. So I've actually drawn this here. So that's the interval AB. It's an open interval, doesn't include the endpoints. And we take away C. So that's why we have a hole in the middle. So this is AB, take away C. So just so it's clear, this x in AB take away C is the same as, well, there's different ways to write it. It's the same as x in AC union CB. And it's the same as x is in AB, but x is not equal to C. Okay, so let's give an example of this. So suppose we have these inequalities. For all non-zero x. So the sandwich is now called U, not F, but these are our GX and HX. So let's draw a graph. So 1 minus x squared over 4 the x-intercepts are 2 and minus 2, and the y-intercept is 1. So the graph of gx looks like this. And the graph of hx goes in the other direction like this. Okay, and let's put another circle here. Put another circle here to show that we're not counting x equals 0. And now we assume that ux is between gx and hx. But it could do anything like this, right? It's a bit crazy. So yeah, it could have any shape like this. But the sandwich theorem tells us that we still know the limit. Then, by sandwich theorem, the limit of ux as x goes to 0 is 1. Note, don't need to know anything else about this function u of x. Oh, let me write this as u of x here. Okay, so another example. And with these, it always helps to make a graph. Suppose 2 minus x squared is less than gx is less than 2 cos x for all x not equal to 0. So again, let's make the graph. So for 2 minus x squared, the y-intercept is 2. And what are the x-intercepts? They are given by plus or minus root 2. So let's draw that. That's not so good. A bit narrower. Try that. Not perfect, but good enough. And what about 2 cos theta, 2 cos x? Well, remember that graph has x-intercept pi over 2, and how do I know that the square root of 2 is less than pi over 2? Well, I know that because if I take this and take square roots, then I get that fact. And that follows because pi squared is greater than 8. So in fact, pi squared is approximately 987. Okay. And we can also see that because there is a power series for cos x. Like this, and so 2 cos x is 2 minus x squared plus something. So you might expect, indeed, the graph of 2 cos x here to be over the graph of 2 minus x squared. Okay, and now gx, we assume, except for this point, which we assume nothing about, gx goes between the 2 graphs. So that now is my gx. Then the limit of 2 minus x squared equals the limit of 2 cos x, which is equal to 2. These are both as x goes to 0. So the limit of gx as x goes to 0 is also equal to 2. Okay, so let's stop there, check if there's any questions just now. Okay, so about this, just a remark. Don't need to know yet. Okay, thank you. So see you next week.